We've already talked about force generation. We're going to look at the mechanisms of skeletal muscle contraction. So essentially the twitch and the two types of muscle contractions. So we're going to speak about the twitch, which is a brief period of muscle contraction. It's like a single unit of contraction. And then later on, we'll get into some of the other factors. This is going to be after the exam that regulate how we generate force. And then we'll talk about some things like velocity of shortening even further along. So today we're really only focusing on the twitch and the two types of muscular contractions. So a twitch can be defined or described as, again, a brief period of muscle contraction, specifically in response to one action potential or one stimulus, right? It's an all or nothing event for muscles at rest. And we know this because we know that the end plate potential, which is what generates the twitch, is either going to happen or it isn't. It's not graded the way that the graded potentials are. It's pretty much like an action potential, right? We also can think about defining or describing a twitch based upon different perspectives here. So we can think about a twitch as a response of an entire muscle fiber, right? One muscle cell to one action potential. We can think about a twitch as being what happens or the response on an entire motor unit to one action potential. So all of the fibers that are being innervated by that one motor neuron. And then we can also think about a twitch from the level of the entire muscle body. So what happens to an entire muscle body, again, in response to one single action potential. And so we can speak about the different phases of a twitch. Right, so basically a twitch is a force generation. And so we can look at the amount of force or tension that's produced and compare that to time and then talk about the phases by which those that force generation changes. So let's talk about the phases of a twitch here. So we start out with the latent period. This is a very short window right after that action potential hits that muscle fiber or muscle body or our motor unit. Remember, we can think about a twitch from different perspectives here. And so right after that action potential arrives, there's a few milliseconds where kind of nothing happens. It doesn't begin to shorten yet because all of the steps we've spoken about as far as excitation and contraction coupling are still getting going, are still warming up, if you will. So we know that calcium has to leave the SR, has to flood the cytoplasm, has to interact with troponin, that sliding of tropomyosin, all of those things have to happen. And so we don't start generating force immediately after the action potential arrives on skeletal muscle. There's a brief latent period. After that period, then we get into the contraction phase. Here we've started cross-bridge cycling. So this is usually the second part of the phases here. This is where we're generating force now because cross-bridge cycling is happening. And we talked about the fact that cross-bridge cycling is not only shortening muscle for the sake of moving muscle, for the sake of mobility, but also for the sake of generating tension, generating force to move physical objects to compensate or to go against or to contract in order to move loads is what I'm trying to say. To move loads, to move things in our environment, right? And so that contraction phase is where that force, that tension is really building up, and the graph shows that rapid rise in the tension. And then we get to the peak, right? So different muscles have different maximum tension or maximum force that they can generate. And when we get to that maximum force, we kind of start dropping off. So here we've got calcium now leaving the cytosol. Here we've entered the relaxation phase. And this is where all that calcium is being pumped back into the SR from the sarcoplasm. And so the muscle can now relax as troponin no longer has calcium bound to it. Therefore, tropomyosin is covering up those binding sites once again. And then the sarcomere can relax and shorten, and the entire muscle can relax and shorten. Okay. So these are the phases of a twitch, and let's kind of draw them out here for some added clarity. And keep bearing in mind that this, again, can happen at one muscle fiber or one muscle cell. It can happen to the entire muscle body, or it can happen to a motor unit within that muscle. And we'll talk about how that can vary a little bit later on. So we're looking at phases of a twitch. And here we're comparing the force that's generated and time. Right, so over here is the force. We can also think about this as the tension in grams, and then the time down here in milliseconds. And so we start off with 0 force, right? The muscle is relaxed here. And then at this point, we can think about 1 action potential. And I'm going to put in brackets EPP because we know that an action potential specific to skeletal muscle produces an end plate potential, really. Okay, so then after that action potential, there's a brief period where nothing changes. We stay at 0, and then we start generating some force. So after everything gets warmed up, calcium is moved over. And let's actually start from the beginning. So the action potential comes, travels down the T tubules, which are coupled to those receptors, pick up that change in voltage, right? We then pass that signal along to the ryanodine receptors. From the DHP receptors to the ryanodine receptors, they open up those channels. Calcium can leave the sarcoplasmic reticulum, flood the cytoplasm, interact with troponin. So that's all the time it takes for that to occur here. Then after we start cross-bridge cycling, we start generating force. Okay, we generate the maximum force that we can, which again is different for muscles depending on how many fascicles are involved, the size of the muscle, the fiber diameter, etc. And then we drop off after that point of maximum force generation. And that is called the relaxation phase. And it lasts much longer than any of the other phases. So it's the longest phase of the twitch. Okay. So we start off with the latent period here. And we said the latent period was caused by the time it takes for excitation, contraction, coupling to get going. So here we have 0 tension or force. Which means that there's no cross-bridge cycling happening just yet. And so this is the lag time that allows for excitation, contraction, coupling. Okay. Then we start generating force. So that's the contraction phase, or the second part of the twitch. And so the contraction phase can really vary in length, depending on, again, what muscle we're looking at, what's the size of the muscle, how many motor units are actively contracting. And this is where the tension is rising. And how far it'll rise, again, will depend on that muscle. And this is due to cross-bridge cycling. Okay, here the force generation reaches its peak. Or the peak of the contraction reaches its peak, I should say. Okay, and then number 3 here, the third phase is going to be the latent, the relaxation phase, which I've drawn here in blue. And the relaxation phase we said is the longest phase. Right, it's the longest phase of the twitch. This is where tension is slowly decreasing or dropping off. And here we've got the calcium ATPase pumps. Removing that calcium from the sarcoplasm. Right, it's going back into the sarcoplasmic reticulum, which is the storage area. So this is what happens in a single twitch. Again, we're thinking about one action potential. We're also reminding ourselves that this can be representative of a motor unit, a muscle fiber, or the entire muscle body, with reminding ourselves that at the beginning here, things are getting warmed up, so there's zero tension or force produced immediately after that action potential. This is where that excitation, contraction, coupling, that series of events is occurring. Then we generate the maximum force that's allowed for this, again, muscle body, motor unit, or muscle cell. We get to the maximum force that's possible. And then the rest of the twitch is really the relaxation of that muscle, which is where calcium is leaving the sarcoplasm, going back, or being pumped rather, back into the sarcoplasmic reticulum, and the muscle can then relax. Okay, so that's a twitch. Let's continue on to speak about some other aspects of the twitch and the different types of twitches. So we've got two types of twitches. We've got an isometric twitch or an isometric contraction. We can think of it as well. And then we've got isotonic contractions. And in order to understand the difference here, let's talk about some of the properties and the components of muscle. So we've got the contractile elements. Now, we spoke about this before. We said that the muscle body, which really comes down to the level of the sarcomeres. This is the contractile part of muscle, also otherwise known as the contractile elements. Then there are the series elastic elements. These are basically the connective tissue that are covering the muscle and covering the tendon and the tendons themselves. These are not contractile, so they're not shortening. They're really just attaching to the muscle, and they're going to be stretching, right? They're mainly connective tissue. They've got lots of elastic fibers, and essentially they can provide the elasticity that can facilitate that contraction, or they can stretch and resist the shortening of the muscle, which we'll see in a little bit. So these are the non-contractile parts of the muscle. There's no shortening of sarcomeres happening in these regions, whereas the actual muscle shortening is happening here in the contractile elements, which is the muscle body, and at a more microscopic level, the sarcomeres themselves. Now we can think about the tension that's being produced. That is coming from the muscle actually shortening, right? So when that cross-bridge cycling is happening and the sarcomere is shortening, the myofibril is shortening, that is actually producing force, right? And that force we can consider tension. We can also think about what that force can do. So I keep mentioning this point, right? Muscles are not only just to move for mobility, but they can oppose other types of weights or loads. And so a force that's generated by a muscle while it's contracting can be used to overcome other forces, which we can consider loads, okay? So if I'm trying to lift something really heavy, and I've got a weight here just for demonstrating purposes, this is the load that I'm trying to lift. And even though it's not very heavy, my muscles are contracting, right? So there's some shortening happening, specifically in my biceps here. And that is producing the tension that's required to overcome the weight of this object, which is considered the load, right? And so based upon that premise, we can think about two types of muscle contraction or two types of twitches. So I've got a question here, excellent question. Is this still considered voluntary? Yes, it absolutely is. And we'll talk about some practical examples that will kind of highlight that. So this is all still considered voluntary. Although there are reflexes that are not voluntary that we're not going to speak about, but there are some involuntary contractions of muscle. Those are like our deep tendon reflexes, which we're not talking about here. These are actual muscle contractions that we decide to make. And we'll talk about some practical examples here in a bit. So isometric contractions, this is where, if you think about the root of this word here, iso meaning same, metric meaning length, this is where the length of that muscle remains the same. Shortening never actually happens. And this is where the load is greater than the tension. Here we see the contractile elements contract, so they're generating force, but the muscle never shortens because the tendons and the other series elastic elements, right, the non-contractile parts of the muscle, are stretching to compensate the tension that's being generated. And so the muscle itself doesn't ever actually shorten, so you are never able to overcome this load, okay? So I'll talk about this illustration, then I'll talk about a practical example that may make a little bit more sense. So here's an illustration. We've got this muscle hooked up to this force transducer. It's trying to overcome this load here at the bottom. The simulator, which is kind of mimicking a motor neuron. So we can think about this connection here being a motor neuron, which is going to, zap this muscle with an action potential, and it's going to generate some force, okay? Now, after we zap that relaxed muscle, it will begin to contract. And we can see that by the bulging or the shortening of the contractile elements of the sarcomeres of the muscle body itself. We can also see, if we compare these series elastic elements here, which are the tendons essentially, to them here, they've stretched out a little bit. And so they're kind of compensating whatever shortening the muscle is doing. And so overall, the muscle doesn't change in its length because the series elastic elements are compensating any shortening that's actually happening in the muscle body. Here, this in a practical scenario, this is if you're trying to lift something that you physically cannot, okay? I watched a couple years ago, America's Strongest Man, or Strongest Man Alive or something like that. And he was able to lift, I think, 1,200 pounds. So he could deadlift, a bar with 1,200 pounds suspended on it, and he could just, lift that straight away off the ground. And if you think about maybe you or I trying to lift that 1,200 pounds, it's for sure going to be an isometric contraction, right? There's no shortening that's happening there. And so you're going to try to lift this 1,200 pound bar, your muscles are going to contract, they're going to generate some force, but it's never going to be enough. And so what we'll see is the tension will rise and rise and rise and rise until the maximum force or tension that your muscles can generate will be achieved, and then it'll drop off and relax. So you will never actually shorten the muscle. In other words, lift that object off the ground because your muscles cannot produce enough force to overcome or to move that load off the ground. And that is considered an isometric contraction. Okay, iso meaning same and metric meaning length. The muscle length never actually changes. In other words, you're never actually to overcome that load. The load is too great for the tension that's being produced. Let's compare that to an isotonic contraction, okay? And we'll talk about how these are never purely one or the other. We'll talk about how this actually happens in a little bit. But an isotonic contraction is different. This is where you can actually overcome the load. You're now shortening the muscle. You're now producing a constant amount of tension because it's enough, right? You don't have to produce any more because you've gotten to a level where it's enough tension to actually move that load. And so the tension, as we'll see here in a bit, can flatten off at that point. And the tension is now greater than the load, and so you can effectively lift that load off the ground, which is, again, more synonymous to me lifting this weight that I've got here, right? I'm going to try to lift it for a period, and then I'm going to generate enough force so that the force can now flatten off, and I can actually shorten the muscle, effectively moving my limb to move that weight off of the ground, okay? And if we, again, look at our little apparatus here, our little illustration, we've got this muscle, again, suspended to this force transducer. We've got a load that now can actually be moved here. We stimulate or zap this muscle with an action potential. It begins to contract. We can see the contracted version or contracted state here, where the muscle actually shortens. We don't see the stretching of the tendons, and the load is actually lifted accordingly, right? If we compare the graphs of what's happening here, the tension will rise initially, right? And this can be considered an isometric contraction while the tension is still rising. But then when the tension flattens off, we've now produced enough tension or force to actually overcome that load. And so we'll produce that tension, constantly at a constant level until the contraction is over, and then we'll slowly relax. And we can compare the graph of the tension versus time to the graph of the shortening versus time, and we'll see that as the tension is enough and that tension is sustained, the contraction or the shortening is also sustained until it's relaxing. And we want to be thinking here that isotonic contractions are where we're actually lifting the load, and we don't see that stretching of the tendons on the ends there. And so this is a really nice summary of showing us how isotonic contractions occur. So we can lift this load, right? Let's say this is a muscle that can only lift 17 grams, right? That's the maximum force this muscle can generate. So if you try to lift 5 grams, it's going to be an isotonic contraction, right? We'll generate enough force and then it'll flatten off and then we'll relax. Likewise, if we try to lift a 10-gram load, the same thing will happen. We'll generate 10 grams worth of tension or force. We'll flatten off because it's enough to lift that load and then we'll relax. Again, we can lift a 15-gram load. We'll generate a little bit more force here, then flatten off and then relax. But if a muscle that can only produce 17 grams of force tries to lift a 20-gram load, it's going to be an isometric contraction. We're going to try to generate as much force as we can, and we're going to keep going and keep going and keep going. It's never going to flatten off because the tension is never going to be enough, okay? And when we get to 17, which is the most that this muscle can physically produce, then we're just going to flatten off. We've never actually shortened the muscle, and this can be considered an isometric contraction. Whereas an isotonic contraction, if you think about the nomenclature here, the word, iso meaning same, tonic meaning tension, there are periods where the tension remains the same because it's enough to actually overcome that load. Okay. And then the last thing we'll talk about here is basically understanding how some purely isometric contractions can occur. So you can try to lift something, but not actually lift it. That's actually possible to be purely isometric, but a purely isotonic contraction is very rare. When you try to lift something, you usually have to build up enough force to effectively lift it before it becomes an isotonic contraction. So even if the load is constant, like let's say I'm lifting a heavy crate of books, maybe 50 pounds or so, I'm going to attempt to lift it for a couple seconds. They're going to be isometric contractions where I'm trying to generate enough force. And then finally, it's going to be an isotonic where I actually move that crate of books off the ground. Okay, so isometric contractions usually precede isotonic contractions, whereas isotonic contractions are usually never purely isotonic or on their own, right? Isometric contractions can be purely isometric. And so that at that point, when I can lift that crate of books off the ground, then I'm generating enough force to overcome the books and the muscle will then shorten. And that is considered an isotonic contraction where the tension will be sustained as it's enough to actually lift that crate of books. We also want to remind ourselves here that the load, when we're lifting loads, the load is not constant. It will change based upon how our limb positions change. And I'm sure a more practical application of this is if you've ever been lifting something heavy, like maybe some grocery bags, if you're lifting them out at the side of your body, they may be perceived as being a little bit heavier on your muscles. Maybe if you lift them across your back or across the joint, they can be perceived differently. So the load is never constant. As our limb positions change, even with the change of position with your gait as you're walking with maybe groceries or a heavy bag, as your limb positions change, then the load will also change. And so the type of contraction can change as well. So you may be lifting something isotonically, but then there's a period where your muscle has to try to generate enough force to maintain that load. And so we can kind of switch back and forth between isotonic, isometric is what I'm really trying to say. As your limb position changes, the load changes and the type of contraction too may change.